Significant figures can be very intimidating when you first learn about them, but in this video I'll take time to break down and organize the rules so they don't seem as overwhelming. Think of significant figures as digits in any rational number that have meaning or contribute to the accuracy of a measurement. As far as defining significant digits goes, all non-zero numbers are always significant. Determining whether or not zeros are significant is the tricky part. The first rule of zeros is, if a zero is located between two non-zero numbers, it is significant. The OpenStax textbook calls this zero captive. In the number 308, for example, the zero is located between two non-zero numbers, 3 and 8, so it is significant. When determining the number of significant figures in this number, we count the 3, the 0, and the 8, which means it has 3 significant figures. For the number 0.4702, the tenths, hundredths, and 10,000ths place all are non-zero numbers, so they are significant. The 0 in the thousandths place is a captive zero, so it's also significant. Therefore, the number 0.4702 has 4 significant figures. The rules are trickier when zeros are leading and/or trailing, so we'll break this one up into two parts, determining the significance of zeros in rational numbers with a decimal point and without a decimal point. But first, let's define leading and trailing zeros. Leading zeros are present in numbers where the first non-zero number occurs after the decimal point. Any zero before the first non-zero number is a leading zero. Trailing zeros can be in numbers both with and without a decimal point. A trailing zero is any zero that occurs after the last non-zero digit in a number. To review, leading zeros can be the first digits in a number, captive zeros are located between two non-zero numbers, and trailing zeros can be the last digits of a number. Let's look at how we determine whether or not leading and trailing zeros are significant in numbers with a decimal point than numbers without a decimal point. When determining the number of significant figures in a number that has a decimal point, read the number left to right like normal. Starting at the leftmost digit, move right one digit at a time until you reach the first non-zero number. Any zero before the first non-zero number is a leading zero and it is not significant. The first non-zero number is your first significant digit. Each digit after is counted as significant, including captive and trailing zeros. Let's look at two examples. 0.042. Starting at the left and moving right, the digits in this number are 0, 0, 4, and 2. The first two digits are leading zeros, so they are insignificant. The first non-zero number is 4 in the hundredths place, and after that is 2 in the thousandths place. Therefore, this number has 2 significant figures. 57.9400. The first digit in this number is a non-zero number, so it is significant. Therefore, every digit after is also significant, including the trailing zeros. This means that every digit in this number is significant. Therefore, it has 6 significant figures. When determining the number of significant figures in a number that does not have a decimal point, read the number right to left. Starting at the rightmost digit, move left one digit at a time until you reach the first non-zero number. Any digit before the first non-zero number, while moving right to left, is a trailing zero, and it is not significant. The first non-zero number is your first significant digit. Each digit after, toward the left, is counted as significant, including captive zeros. Let's look at two examples. 95. Starting at the right and moving left, the ones place digit is 5, which is a non-zero number. Therefore, it is significant, and so is every digit to the left of it. The number 95 only has one more digit to the left of the first non-zero digit, so it has 2 significant figures. 78,210. Starting at the right and moving left, the ones place digit is a trailing zero, making it insignificant. The tens place digit is a non-zero number, which means every digit to the left of it is significant. In this case, there are 3 digits to the left of the first non-zero digit. meaning this number has 4 significant figures. Now let's check our understanding with a few examples. Now that we know how to count the number of significant figures in any number, let's look at how they apply to mathematical operations. When multiplying or dividing two or more numbers, you should round the final answer to have the same number of significant figures as the factor with the fewest number of significant figures. Here's an example for clarification. 12.9 times 6.357 is 82.0053. This number rounds to 3 significant figures for a final answer of 82.0 because 12.9 has 3 significant figures, which is fewer than 4 in 6.357. When adding or subtracting, you should not be concerned with the number of significant figures in a number, but the number of digits after the decimal place. You should round the final answer to have the same number of digits after the decimal place as the number being added or subtracted with the fewest digits after the decimal place. Here's an example for clarification. 12.9 minus 6.357 is 6.543. This number rounds to 6.5 to have one digit after the decimal place because 12.9 has only one digit after the decimal place versus 3 in 6.357. It is important to note that when you do several operations before reaching the final answer, you should not round any number before the final answer. Also, follow the same rounding rules you've been taught since elementary school. If the value of the dropped digit is less than 5, round the retained number down, and if it's greater than 5, round the retained number up. However, if the dropped digit is 5 and either it's the last digit in the number or there are only zeros after it, round so the retained number is even. When rounding a number with a decimal point, make the last digit in the number the final significant figure. When rounding a number without a decimal point, round at the number of desired significant figures, then add zeros to make the rounded number have the proper number of digits. Think of this like 10 being a different number than 10,000. Both have the same number of significant figures, but they are very different numbers. Let's look at some examples to understand rounding rules. When taking measurements in a graduated cylinder, you must know how to read the volume correctly in order to succeed in lab. If the graduated cylinder marks by tenths of a milliliter, record your measurement and estimate to the nearest hundredth of a milliliter. As a general rule, estimate one digit past the graduated cylinder's markings. You should make your estimation based on the meniscus. The meniscus is the lowest point on the curved surface of a liquid, as pictured here. As an example, the measurement of this picture should be read 6.60 milliliters. The same rules apply for taking measurements of weight on a scale. If the scale is digital, the last number that is reported is the only uncertain digit.